The hydrogen igniters under the orbiter's engines have now been armed. These devices are used to ensure that any hydrogen flowing through the engines prior to ignition does not accumulate. T-minus 45 seconds. 14 seconds away from switching command to the onboard computers. The Space Lab countdown is now complete. Coming up on the 30-second point, and we go for auto sequence start. The SRB hydraulic power units have started. These move the solid motor nozzles to steer the vehicle. T-minus 20 seconds. 18, 17, 16, 15, 14, 13, 12, 10. We have go for main engine start. 8, 7, 6. We have main engine start. 3, 2, 1. Solid motor ignition and liftoff. Liftoff of Columbia and the first flight of the European Space Agency Space Lab. The shuttle has cleared the tower.
Roger, roll. Vehicle rolling from tail south around to 35-degree azimuth northeast. Roger. Altitude 1.1. All APUs running at 106% of RPM. Distance 1 mile, 2.7 nautical miles altitude. 5 miles altitude. Roger. Columbia, Houston, your go and throttle up. Throttling up from 85% back to the 488,000 pounds of thrust that each of Columbia's new engines has. We're 13 miles altitude, 10 miles downrange. Each of the three fuel cells producing 7.8, 7.2, and 7.2 kilowatts, respectively. 25 miles altitude, 26 miles downrange. Roger, SRB set. SRB has separated. SRB engines have pulled away from the spacecraft at this time. Columbia, Houston, first stage performance nominal.
We finally made it to orbit and opened up the payload bay doors and deployed the radiators and put out the KU band antenna, and we were ready to operate in a really short time. And this gives you an idea how easy it is to get around in there. You just float in and out of the seat, and this is a configuration on orbit with our little computer that told us where we were in the world, and one CRT running most of the time, and alone on the flight deck while the other guys are busy doing science. And John's taking pictures out the window there with a 35 millimeter camera and a 105 millimeter lens on it that we borrowed from the guys in back. And once we got the hatch open, the science crew started heading back to the Space Lab to crank it up, and they'll tell you about that.
Here we are, we're just floating back to open up the Space Lab hatch and now enter the Space Lab for the first time. And it was just the way we left it on the ground. Not a thing had come apart, and it looked almost like home, just like our trainers would have been over at the Marshall Space Flight Center in the payload crew training area. And felt very, very comfortable moving on in here and beginning to activate the Space Lab. Have a few valves to throw and various pieces of equipment to turn on. And let's see, I guess we're just going through some...
Sal.
Oh yeah, this is SAL operations here. Scientific airlock is about a 1 meter aperture that we first of all opened up the lower hatch right here, and then we cranked the table down, which we'll see turning on that handle in the upper right hand corner. and this lowers the table down into the module, and then we can take off some grounding straps necessary there for launch that you can see coiled up right on the front, and then begin to mount our experiments to it. And so that's the table on which we extended 2 different experiments into space. One of them associated with a Japanese experiment had diagnostics equipment to look at the plasma surrounding the vehicle, and then the other one was a very wide field camera to take photographs of the stars in the ultraviolet. And so we've now in the process of closing it back up, putting the lower hatch, the inner hatch, back onto the scientific airlock, and then after that's completed, we would open the outside hatch and extend the experiments on into space. It's very easy to move that lower hatch around, inner hatch, in weightlessness, much better than it is on the ground. Here's a view showing the outside hatch now opening up to expose that 1-meter diameter chamber. And after the outer hatch is laid back fully 180 degrees, then we'll see the experiment table with the experiments on it, then cranked out into space. And the first thing that we're extending here is the diagnostic package for the Japanese experiment, and that can then be exposed to the plasma directly out into the environment and measure what's going on. Here's just a brief glimpse showing ham radio or amateur radio operations. Looking out the overhead window and holding the little transceiver unit just about the size of the portable walkie-talkies that we use for communication within the spacecraft. Slightly different power level, slightly different frequencies, about the only difference. And on that, we're able to communicate all around the world. This is a shot from the inside the Space Lab, just showing work at a couple of our computer keyboards. We have one computer keyboard on each side of the Space Lab interior, and then a number of experiments. That's a Japanese experiment showing a plasma jet. Those pulses come out at about every 15 seconds or so, and we can look at vehicle charging effects and interactions with the medium around the spacecraft. So we're now doing more experiments on the inside. Why don't I turn over to one of you fellows to continue? Continue the narration here.
On the left side of that video picture here, you see the fluid physics module, which is a machine to study the behavior of liquids under weightlessness conditions. See it here, it looks a little bit like a Fiat engine. The idea is to understand liquids because all the material sciences experiments like growth of single crystals or the production of new alloys deal with liquid material, with liquid metals. And that machine allows us to use silicon